Hello, in this video we'll be looking at gravitational force. So that's gravity. We'll be looking at gravitational fields, and potential energy. Potential. Okay. First of all, we'll talk about the force between two objects. So, let me draw 2 point masses. Okay, point masses don't really exist as such, but they are approximations to point masses, and they will be attracted to each other due to the force of gravity. So, that will feel a force F pointing in that direction, and this point mass will feel a force acting in that direction, also of magnitude F, but in the opposite direction. So let's call this one here M1 and M2, and they form Newton pairs. They are equal and opposite, same type of force, and obeying the Newton pairs, of course, from Newton's third law. So now the force between them is equal to the universal gravitational constant. That's a constant you can look up in your data booklets, multiplied by the mass of one times the mass of the other, divided by r squared, where r is the distance between the 2 point masses, and that gives you the force. Okay, so that's for point masses. Now let's make it a little bit more real. I'll rub this off. And so what would be the force between real masses? So we'll make them spherical masses, a bit like planets. Again, we'll make them the same size. These are solid masses. Again, we'll call it M1 and M2 being solid masses. Now the distance then is between them will be the distance between their centres, like that. So the distance between them is r, that's between the centres of these masses, and they both feel the force F, and the force that M1 would feel a force F, that would also feel a force F. Equal and opposite forces, and the force again would be gravitational, the universal gravitational constant times M1 times M2 divided by the distance between them squared. Okay. Now, if these were planets, say the Moon and the Earth, we wouldn't need to worry about the bit of the R that's going into the centre. If they're so far apart, all we need to worry about really is the distance between their surfaces. Now, often when we're talking about gravity, we talk about large objects, because that's when you really feel a big force, and a large object very close to us and very near and dear to us. Now let me rub the title off to give us a bit more space, is the Earth, and that has a gravitational field around it. So let me draw. This is the Earth. Oh, not too bad. That's the Earth. Now, and let's think about what the force field will be. Now, the force field would be acting towards the centre of the Earth. So you'll get field lines acting towards the centre. If I draw a point there, it makes them easy to draw. These field lines will act towards the centre of the Earth. Now, because gravity is only attractive. We don't need, not like electrostatic. We can be positive or negative. They all act towards the centre, and these field lines, heavens, I think I drew a little too many. Never mind, like that. So those are the field lines. Now, again, it's called the Earth. Now the Earth is a solid object, and yes, you will get gravity field lines within the solid object, but generally speaking, well, we don't really need to, on our course, worry about how the field lines behave within the Earth, just on the outside. So we draw it like that. They behave differently inside, and even theoretically it doesn't quite work because the density changes. So now, there we go, those are field lines pointing in. Now if we have, notice, if we have an object here, okay, I'll call an object there, call that object A, another object B. A will feel a greater force field than B because the lines, the field lines, are closer together. They're more dense. Okay. Now, those field lines can be represented by the force, the gravitational field strength, rather gravitational field strength. And let's take from the middle, and let's go out, and let's say to another point, say from the very centre to a point P there, and a distance r away. And so we're going from centre of the Earth to distance P away, so point P, distance r away, and there we'll get a certain field strength called the gravitational field strength, and the gravitational field strength is called G for gravity, and that is equal to F divided by M, and M is the pointer mass. So there we go, that is the field strength at any point a distance r from the centre. Okay, now let me rub this off because it's a bit busy, and there we go, we have field strength G equals F over M. Now if you remember, F was equal to M1 M2 times G divided by R squared. Now when we're dealing with, the way I like it, when we're taking with a small mass, a big mass, I like to call that as big mass M, and this is small mass little m. So therefore I would write that as G big M little m over R squared. I do that to distinguish between a small particle and the Earth. So therefore the gravitational field strength at a point P of a small mass, a distance r from it, would simply equal to F divided by M. So all this divided by M, so the M cancel out, which gives you G M over R squared. In fact, that of course is G. That's the gravitational field strength. Okay, so as we see, the further we are away from the Earth, with the r the distance, the smaller the gravitational field strength, which makes sense, and the bigger the mass, the greater gravitational field strength. However, we stop at the surface. We don't go further in than that because it changes everything. Now, the next thing we'll look at is gravitational potential. Gravitational potential, and this is denoted by V potential gravity, Vg. So here we are. Here is the Earth. Okay, these are some field lines pointing towards the centre, and around it you have some potential concentric circles of potential. So I'll colour this in solid, so you can tell this is the Earth. And around here, at right angles to the field lines, I'll draw a few more field lines in. At right angle to the field lines, you'll get concentric circles of potential. Okay, these are lines of potential. Now, they actually get negative values. I'll explain that in a bit. So these are the potential equipotential lines around it, and the formula for the gravitational potential is equal to minus G times the mass of the planet, which I call big M, divided by R, where R is, let's take a point from it. I'll take it from the centre of the Earth, and R is a point, say P, a distant R from the centre of the planet. That gives you the lines of equipotential, and it's negative. This is a little bit strange, isn't it? Now I'll stop the video here, and in the next video we'll talk about why it's negative.